Hello everyone, I am B. Chiranjeev Rao, Assistant Professor, Electrical Engineering Department at Sri Shankaracharya Technical Campus, Bhilai. I welcome you all to the course on Industrial Automation Drive. As in previous sessions, Dr. Shimpi Rahlan had discussed a brief introduction about electrical drives, what are the different types of drives, the various function of drives, and also the four quadrant operation of the electrical drives. So, today we will begin AC drive control. So, let us start with the introduction of AC drive control. Primarily, electrical drive are divided into two groups, AC drives and DC drives. So, first we deal with AC drive control system. An AC drive is a device which used to control the speed of an electrical motor in order to enhance process, control, reduce energy usage and generate energy efficiently, decrease mechanical stress on motor control application. AC drive is also called as variable frequency drive or variable speed drive or adjustable speed drive. AC drive used to control speed and torque of an AC motor by varying the frequency and voltage applied to the motor. First, we start with speed control of induction motor using electrical drives. The various method of speed control through semiconductor devices are as under. First, by adjusting the stator voltage. Second one is by adjusting the frequency of the source. Third one is by adjusting the resistance of the rotor circuit, and last one is by injecting slip frequency EMF to the rotor circuit. So, first we will see control of the induction motor by stator voltage variation. Stator voltage control is a method used to regulate the speed and performance of an induction motor by adjusting the voltage applied to its stator windings. This technique is commonly used in application where precise speed control is required. The stator voltage can be varied from 0 to full value within the triggering angle range. By reducing stator voltage, speed of a high speed induction motor can be reduced by an amount which is significant for speed control of some fan and motor drives. The speed torque curves of this control is shown in the figure. While torque is proportional to voltage square, current is proportional to the voltage. Therefore, as voltage is reduced to reduce speed for the same current, motor develops lower torque. Consequently, method is suitable for application where torque demand reduces with the speed which point towards is. Consequently, method is suitable for application where torque demand reduces with the speed like fan and pump drives. Variable voltage for speed control is obtained using AC voltage controller. Now, next topic is stator voltage regulator, in which we first see voltage adjustment. The regulator adjusts the voltage supplied to the motor's stator. This can be done using devices such as auto transformer, variable transformer or electronic controller. Next is torque control. Reducing the stator voltage decreases the magnetic flux, which reduces the torque produced by the motor. Increasing the voltage increases the flux, therefore the torque. Next is speed control. The speed of the motor is related to the frequency of the supply voltage and the flux. Lowering the stator voltage decreases the flux, which typically leads to the reduction in the speed. Domestic fan motor, which are always single phase, are controlled by a single phase track voltage controller shown in the figure. Speed control is obtained by the varying firing angle of the track. These controllers, commonly known as solid state fan regulators, are now preferred over conventional variable resistance regulator because of high efficiency. Industrial fan and pumps are usually driven by three-phase motors. The figure shows a commonly used thyristor voltage controller for speed control of three-phase motor. Motor may be connected in star or delta. Speed control is obtained by varying conduction period of the thyristor. For low power rating, anti-paralleled thyristor pair in each phase can be replaced by a track. So, next topic is variable frequency control. Variable frequency control of induction motor is a technique used to manage the speed and the torque of the motor by adjusting the frequency of the electrical power supplied to it. This method is commonly implemented using variable frequency drive. When either V saturated or reach rated value at base speed, it cannot be increased with frequency. Therefore, above base speed, frequency is changed with V maintained constant. When voltage V maintained constant, maximum torque decreases with increase in frequency or speed. Variation in terminal voltage with frequency is shown in the figure. Now, next topic is constant volts per or V constant volts per hertz or V by F control. This method is generally used to regulate the speed and torque of an induction motor by maintaining a constant ratio of voltage to the frequency. This technique is commonly implemented using a variable frequency drive to achieve efficient motor performance across various operating conditions. How constant volt per hertz control works. First, speed control. The speed of an induction motor is proportional to the frequency of the AC supply. By varying the frequency, the motor speed can be adjusted. The V is kept constant above base speed. Below the base speed, V by F ratio is maintained constant, except at low frequency where V by F ratio is increased to keep maximum torque constant. Corresponding speed torque curves are shown in the figure for both motoring and braking operations. To maintain efficient motor operation and avoid overheating, the motor's magnetic flux should remain constant. The magnetic flux is proportional to the voltage to frequency ratio. Maintaining a constant V by F ratio ensures the motor operates with stable flux regardless of the speed changes. The curve suggests the speed control and the braking operation are available from nearly zero speed to above synchronous speed. A given torque is obtained with a lower current when the operation at any frequency is limited between the synchronous speed and the maximum torque point, both for motoring and braking operation. Since the voltage can be varied to maintain the constant flux, constant torque operation is possible up to a rated frequency. Beyond the rated frequency, the voltage remains at its rated value and the machine operates in flux weakening mode. The motor gives constant output at all speed and is called constant horsepower mode. These modes are shown in the figure. The figure shows the constant torque region and constant power region. In constant power region, the voltage V is remain constant and torque is decreasing, as you can see in the diagram. Now, next topic is control of the induction motor by voltage source inverter. Voltage source inverter control of induction motor allows a variable frequency supply to be obtained from a DC supply. Figure shows a VSI employing transistors. Any other self-commutated device can be used instead of transistors. Generally, MOSFET is used in low voltage and low power inverter. Power transistor are used up to medium power level, and GTO and GTO and IGBT, that is insulated gate commutated thyristors, are used for high power levels. Voltage source inverter control of induction motor can be operated as a stepped wave inverter or pulse width modulated inverter. When operated as stepped wave inverter, transistors are switched in a sequence of their number with a time difference of T by 6, and each transistor is kept on for the duration T by 2, where capital T is the time period for one cycle. The resultant line voltage waveform is shown in the figure. In this method, the harmonics are reduced, low frequency harmonics are eliminated, associated losses are reduced, and smooth motion is obtained at low speed. Also, when inverter is operated as pulse width modulated inverter. The figure shows voltage waveform of sinusoidal pulse width modulation. The variable frequency required for the speed control of three-phase AC motor is obtained from a three-phase inverter. To avoid magnetic saturation and to obtain constant flux condition in the machine, the voltage fed to the motor must be varied. Therefore, an inverter feeding the three-phase motor must be capable of providing a variable voltage and variable frequency supply. Since the voltage is controlled quantity, in this case, these are called voltage source inverters. When the voltage control is done external to the inverter, the line side rectifier must be a phase control one. By varying the firing angle, the output voltage of the rectifier and hence input voltage to the inverter can be varied. These are called square wave or variable voltage inverter. If the voltage control is available in inverter itself, the input voltage of the inverter is constant and simple diode rectifier be sufficient on the line side. Voltage source inverter is a kind of DC link converter which is two-stage conversion device. They provide a variable voltage, variable frequency supply from constant voltage, constant frequency means and two-stage conversion device. A three-phase supply is first rectifier using a rectifier on the line size. The rectified DC is inverted to AC of desired frequency by an inverter on the load side as shown in the figure. The three-phase AC is converted to constant DC by diode rectifier. The voltage and frequency are both varied by PWM inverter. The circuitry between the rectifier and the inverter consists of inductor L and capacitor C are called as filter circuit. The inverter uses PWM for voltage control and hence is called a PWM inverter or constant voltage inverter. The inductance in the DC link smoothens the current while the capacitor maintain voltage constant. The DC voltage of the inverter is normally obtained by rectifying a 50 Hz supply using a bridge rectifier. So, first the AC supply is converted to DC using a control rectifier and again this DC is inverted to AC using an inverter and is fed to the DC motor. Frequency of the inverter operation is varied by varying T and the output voltage of the inverter is varied by varying DC input voltage. When supply is DC, variable DC input voltage is obtained by connecting a chopper between DC supply and the inverter. The rectifier and the inverter are interconnected by means of energy storing elements. These provide a kind of decoupling between the rectifier and the inverter. Such converters are known as DC link converters. When supply is AC, variable DC input voltage is obtained by connecting a control rectifier between AC supply and inverter. A large electrolytic filter capacitor C is connected in series DC link to make inverter operation independent of the rectifier or chopper and to filter out harmonics in DC link. The capacitor across the inverter maintains the constant voltage. The figure shows output voltage waveform for sinusoidal pulse width modulation. Since output voltage can be controlled by pulse width modulation, no arrangement is required for variation of the input DC voltage. Hence, inverter can be directly connected when the supply is DC. Now, next topic is current source inverter induction motor drive. A current source inverter induction motor drive is a type of power conversion system used to control the speed and torque of an induction motor. Unlike the more common VSI drive, which control the motor by adjusting the voltage, the CSI drive control the motor by regulating the current supplied to it. A thyristor current source inverter control of induction motor is shown in the figure. The diode D1 to D6 and capacitor C1 to C6 provide commutation of thyristor T1 to T6, which are fired at a phase difference of 60 degree in the sequence of their number. The figure shows the nature of the output current waveform. Inverter behave as a current source due to the presence of large inductance LD in the DC link. Current is allowed to flow through the phases of the motor by control of the inverter, and therefore motor current is a quasi current waveform. In a DC link converter, DC link current control the inverter is called a current source inverter. The variable DC link voltage is converted to current source by means of the inductance. The drive shown in the figure can have regenerative capability and 4-quadrant operation if a 2-quadrant chopper providing current in one direction but voltage in either direction is used. In the figure, the phase control rectifier gives out controlled DC voltage. Inductor LD converts this voltage to constant current. The current source inverter regulates the output frequency and thus the torque and speed of 3-phase induction motor. The maximum value of DC output voltage of fully controlled rectifier are so chosen so that motor terminal voltage saturate at rated value. When the inverter frequency is reduced to make the synchronous speed less than that of motor speed, machine work as generator. The power flows from machine to DC link and DC link voltage VDC reverses. If fully controlled converter shown in the figure is made to work as an inverter, the power supplied to DC link will be transferred to AC supply. The regenerative braking will take place. Thus, no additional equipment is required for regenerative braking of current source inverter drive. Change of phase sequence of current source inverter control of induction motor will provide motoring and braking operation in reverse direction. The application of CSI, it is generally used in high torque applications such as in heavy duty motors and industrial machinery where high starting torque is reduced. And other application is pump and fans used in system where high torque is needed at low speed or in variable load condition. Another applications are elevators and cranes. Applications that benefit the precise torque control and high overload capability. The cyclo control of induction motor allows variable frequency and variable voltage supply to be obtained from a fixed voltage and frequency AC supply. A variable frequency supply for feeding a three-phase motor can be obtained from a cycloconverter which operate on 50 Hz supply and provides a variable frequency supply at output. A half-wave cycloconverter control of induction motor is shown in the figure. A cycloconverter can be used. Smooth motion is obtained at low speeds. A phase control of line commutated cycloconverter provides a variable voltage. The firing angle is varied over the period of the input voltage. The output voltage is made up of segments of the input voltage. The voltage control is possible in the inverter itself. The drive has regenerative braking capability. Full quadrant operation is obtained by reversing the phase sequence of the motor terminal voltage. Since cycloconverter employs large amount of thyristor, it become economically accepted only in large power drives. The nature of the cycloconverter output voltage waveform is shown in the figure. This drives has regenerative braking capability. Full 4-quadrant operation is obtained by reversing the phase sequence of the motor terminal voltage. Since cycloconverter employs large number of thyristor, it become economically accepted only in large power drives. So that's all for today's lecture. Under this section, we had covered various method of speed control of induction motor, like by adjusting the stator voltage, by variable frequency control, by voltage source inverter, by current source inverter and cycloconverter. So, in the next lecture, we are going to learn about the remaining part of the AC drive, and in which we will discuss rotor resistance control, slip energy recovery scheme of induction motor and synchronous motor drive. Thank you for your attention and engagement in this lecture. Keep learning.